So the talk that I have prepared is an overview of linear optics, and just to start with the example. When you ask yourself, okay, what is a linear optical problem? So this is what you need. You have system. In this case, you have a picturized like a solid surface, solid system that is perturbed by an external electric field, and what you look is response, the optical response of the system. Here, as you can see, I just write the polarization as a function of the susceptibility Chi1 and the one electric field. And here is the linear response. So this is the starting point. But in nonlinear optics, what you do is, you increase the intensity of the electric field. So the electric field becomes much more intense. It kicks more your system. And so the response of your system now, you see, will depend on two electric fields, so second order in the electric field, to another quantity, which is the second order susceptibility, which is quadratic. And then again, if you continue to increase, you can go to the third order. This is perturbation theory. You can have this Searle function in the electric field, always this quantity phi is the electronic, let's say, the susceptibility. And you can arrive to kick too much your system, in the sense that your laser field can be so intense that you cannot use perturbation theory anymore, but you have to go beyond perturbation theory. There are strategies, but what you have to do is to solve the time-dependent Schrödinger equation. So we will review a bit this stuff, and in particular, again, I put some basis. So I start with this picture, and in this picture, so I will use quite often this scheme. So this scheme is just a graph state, just your valence band. You have a conduction band for side states. And this again, it's part of the linear response. You have a starting point, and the idea is to add the photos, the response. And you see that the polarization again is split in terms of the susceptibility. And what I showed here, just as an example, by the way, an original example, as you can see, there are many people that have been working on this today, is the silicon system that have been used quite a lot as theory development, because there is a good experimental stuff, and for other approaches like hybrids. Very recently, there are people that are using TDF, generalized TDFT with hybrids. So just to give you an example of the starting point, but the talk we are talking about, I want to talk about nonlinear optics. I will focus mainly on one of these processes. So I am in perturbation theory, so the field will be imaging like this. And then this is one possible process at the second order nonlinear optics, which is called the second harmonic generation. That I picturized like two incoming photons, and that interacts with your material, and the response, what you measure here, there should be a 2 omega approaches. And you have this like this. The response is depends twice the two photons that are just. The response in this case is quadratic in the electric field, which depends on the susceptibility, second order susceptibility, and also these are used quite often to the seminar. So omega of the two incoming photon, and minus 2 omega is the photon that just outside that you measure basically. Why, in particular, I focus on this process? Because it's one of the most important. I'm not saying that it's the most important, but it's certainly one of the most important. It's very often used because it's very sensitive to the symmetry of the system. So it is really used as a probe to detect crystal orientation, defects. Here just listed some of the applications where this process can be interesting. And it is often used, very often used in photonics, electronics devices and so on. In particular, I would like to show you some features of second harmonic generation. And when I started to think, well, what I take, I decided in particular to focus, but I won't talk about it because Mirta will talk later. But with Yanko, there are really very nice work that have been done, second harmonic generation, on 2D materials. So I will show you some important features, like, for example, excitonic effects, electrical parts of layer, and different ways with symmetry, crystal symmetry. For transition metal homogenites, again, because I really think that there are quite huge and important literature of people that working with Yanko on this subject. And I will also talk about another system, to use an example, which is Sierra 203, which is an antiferromagnetic system, which in principle, in any central symmetric system, we expect to have the second harmonic generation signal 0. Because of the properties, because of the symmetry properties. And what is nice to show you as an example is that when you calculate Chi2, Chi2 can contain different things. It can have some electronic part, ionic part, but also you can have some magnetic part. So it can be a quite complicated response. And in CR2 is important for the magnetic part, which is just an example. Okay. So this is the first example, and again, probably don't, but this is more of the expertise of Yanko, but I was thinking it was nice to overlap. But I took this example because if you take the monolayer, is a kind of layer system, and you have a look at the band structure, you can see this is just a zoom of these 2 points in the band structure. You can, these are equivalent basically, so you can just look on this part on the left. You can see that there is this, let's say this, because of the spin orbit coupling, maybe you have this shift, the bands, and you can have this exciton that are generated because of coupling. And you have this A exciton, which is really this transition from the upper valence bands to the conduction, and this in the B exciton. Again, I don't want to enter very much details on this, but just to tell you that it has this kind of system, have a electronic structure that presents some nice exciton that follow a certain Rydberg series that I just named here. And in an experiment, this is not yet, this is not yet the second generation. This is just to tell you that have been measured some excitonic effect to identify this exciton, these 2D materials. And what I want to put in evidence is that excitonic effect can be strongly important for the second harmonic generation. So if you have a material and you are measuring or calculating second harmonic generation, you expect to have some enhancement around these exciton, around these excitons. So the importance when you calculate second harmonic generation of the electronic structure, this is what comes out from many studies. Ula, Nicola, posso la batteria il caricatore di è nel mio my apologies, I didn't realize that I was out of battery. No question. Yes. Thank you very much. But
On three sides. So that's the output frequency.
yes, yeah, exactly. Yes, yes, yes. Thank you. And sorry, please. Then the other thing that it was nice with this material and with second order generation is that, as I told you, it's very sensitive on symmetry. So, for example, here I just want to show you this is another actually materials that will generate growth on this substrate, and there are layer, and so on. And here, what you can see here is the second organization. You can see that you see this oscillating. And this is it depends on the layer and it depends on the symmetry. So again, you can see in ASIC, for example, the importance of symmetry, second organization. You have to remember a layer that is symmetric, so you expect not to measure anything, but if you're the same layer, the top B layer, you can direct symmetry, the center symmetry, and you can measure something, and so on. And here, this was another example, but just because when you measure, when you calculate, I say measure and calculate just to say that okay, you are using YAML, so at some point you maybe you do application and you you have to compare with some physical problems, and so you have to know what you're comparing with. So it is not just the output, but you have to pay attention when you compare, if the comparison, the K2 that you compare with is just electronic, or maybe, like in this case, there can be some effects also on the substrate. This was an example of one of these layers that was single waveguide. And what was nice is that you can see a strong enhancement between the free and the waveguide. Okay, and these can be due to different effects between them, interaction, lens enhancement, the phase matching, okay, and or just the strain, for example, that can be created between the two layers. And these are sums to electronic structure, the effect of the layer, the effect of the symmetry, quantities or effects that is to be considered when you do calculation, you want to compare with something that is real. This was also another thing that I found, but again, near target, I mean, it was interesting for me to see things that are really done in YAML. Also by the developer. This was an example of an article that I like because it is, again, there are many factors that can influence your measurements, and therefore, when you do your calculation, you have to take into account that, okay, what you are comparing. This was nice because for me, they basically, the comparison between the different 2D materials is for the same food. So it was nice to have this, in particular, to choose these experiments. You have basically identical lateral condition, identical effect avoided, sorry, effects of strain and grouping, and the substrate is the same. They are really similar mechanism, so the principle I can compare. I also found some other things in literature, and again, type 2 can have many effects, can contain many things, and it is sometimes to pay attention to compare, okay? And for example, if you have a look at our experimental, just experimental, you can see that you can have a fluctuation of value because it depends really on the condition. So if you go on detail in literature, you can really see that the conditions are very different, can be very different. Which none of them is wrong. So just maybe one there is a effect, maybe some strain, maybe some other things. But, and what the other thing that I would like to show is, okay, we have, I just chosen these 2D materials to point out some electronic properties and some importance in the response, but how these compare with the standard materials for secondary generation. And then here you see in the bottom of this table, I put gallium arsenide, BBU, KTP. These are other materials that are currently used in devices. And then you can see how you can compare the magnitude of the secondary generation, and also the fact that you can, through some manipulation, okay, also enhance what is already measured, for example, the QT from this particular fact. This was just an overview. And up to here, what is the message? The message is, okay, we have this second generation, this second linear process. There can be effects of exciton, there can be structural effects that enters in the K2. The K2 that you can calculate is younger. But if you take if some experiment comes to you and asks you, okay, can you do this calculation? So maybe the material that propose you can have also some magnetic effects. So in your K2, so in your response, you have to be able also to include these magnetic effects. So this is an example of CR2O3, which in principle it's a material that has no is centrosymmetric. So as this centrosymmetric, you expect that when you measure SAG, there's nothing. And it's true. It's like this. But if you put your system to a temperature that is lower than certain temperature, is a nil temperature, it becomes anti-ferromagnetic. This is what it means, that the total magnetization of your system is zero. But if you look at the sublattices, this is what you have. You have the spin that starts to be oriented. And for example, these two are exactly the same. I just use two different orientations to make more clear the picture, I hope. So these are the unique cells. So you have the chromium and the oxygen, and you see that for a temperature lower than this nil temperature, you have this spin that can be aligned like this or like this. So you have kind of two sublattices, two chromium that is spinning one side, and the other two chromium that is spinning the other side. Which means that if you calculate this vector L, which is called, which is defined like the difference between the magnetization of this unit cell, the spin that comes out of this unit cell, you can have a vector that points along one direction, or you can have a vector that points in the other direction if the spin, just the spin, okay. Okay, so you have your system, you imagine you decrease your temperature, you have also temperature below the nil temperature, and you can have this kind of, you can have up, down, or you can have down, up, down. But you have two domains. You are breaking not the crystal log, the space symmetry, so the crystallogic symmetry for changing the position of the atoms, but you are breaking another symmetry vice versa for magnetism, and you see this in second generation. In particular, it has been seen that you can observe the domain. In the domain are in particular clearly seen if you use a circularly polarized light. This is why I put this plot. And what you have is red and is blue. So the red basically is a right-handed circularly polarized light, and the blue is left-handed. So you change. Okay, this is the light that you send to your sample. And in this case, the domain is just a domain that I call minus. So it will be just one of the two domains that I just showed in the slide. And you see that in one case, you have the domain minus. You have the left-handed, so the blue. It's much stronger, the signal, than the red. So just to have the qualitative idea of what is now. Which means that there is a second-order generation. So you can measure the second-order generation for a system that is centrosymmetric because of magnetism. And so when you calculate, so if you take the challenge to calculate this, the susceptibility that you calculate has to contain not only the electronic structure information like before, but also the information from the magnetism. So this was an overview of SAG, as I told you. You tell me if I can. Because I really spent some time on this because it's really very important process and also the calculation. It's very advanced. There are many nice things that you can do. But there are other processes, linear process. One of these is, for example, a closed quantum site and maybe faster. And this is a linear electro-optical effects, LEO. Very nice. Okay. And here what you have. Again, I start from the basic, okay, from the basic. So the starting point, linear response. This is linear response. The picture here is linear response. You have one photon, you have the polarization, P1, field, fourth order susceptibility, omega, nine photon, omega fronts, and omega fronts. Then what you do here? Well, you apply another field. But in this case, so you have two fields. But one of these fields now is static. Okay, so omega equal to 0. This what and I visualize this here. So you see that fields. But one, not like before in second generation, is static. What you have is a second order response. So you have a second order peak, okay, second order polarity, where you have a high Q, so you have a second order response, but you see here you have omega 0, which are the frequency of the incoming field, and minus omega, the frequency of the outcoming field. And basically, what these two mix together? We have something from the first order, something from the second order mixed together. What change? It changed epsilon. Basically, the electric function change. You have these things that add to the normal linear response electric function. You have this electric function that I labeled with this epsilon k, which is the static field that I have in here. And these change your linear response, because it's not anymore linear response, because there is a linear response plus some effect that comes from the second order response. Here just an example, so the black one, these are calculation. You can see there is the black one is the standard linear response epsilon xx, epsilon xx. And then these other that comes out are the effects of Leo. That of course is very small, so I have to make these times 150 bigger to see, but they are not zero. They are supposed to be 0, but they are not 0. You notice also here that I put electronic and ionic, because also in this case you can have some electronic and ionic that affects your response. You can find yourself, okay, but it's really small. But even if it is really small, this smallness is anyway significant to make some change in the fractal index, and it is largely used, this effect is largely used in devices, optical devices. There is another one, so I changed, another postlet, which is e-fish. It's a nice name. electron field induced second generation. And this is that what you do, you mix second order with third order. You have this starting point, and here before we are starting from linear response, and we have the second order response. Here we start from second order response, so second order generation, and we have another field. So we have a static field, we have three fields, okay? So third order response, the two added together, so the total polarization of your system is a sum of second order plus third order response. And then what you can see, for example, is that you can really measure it. This was, again, I took from literal this case, where you have this B-layer to the system that is, in principle, the measure and also the calculation is 0, this guy too, second order generation. And this, because it's centrosymmetric. And these correspond, I just write it here, is minus 40 volt, centrosymmetric is here. So basically you don't see anything, and this is the red one. Sorry, minus 20. My fault, sorry. And then if you apply this field, subfield, you have some effects, third order effect, and you see something. You can measure something, and this is due to a third order response of your system. This was just an overview. There are many other processes that in the non-linear optical process that can be measured and described optically with perturbation theory. Some of them I have been talking there, so SAG, video, Richt, but there are other. And I know that in YAML there are also some two-particle absorptions. There are some Mirta will tell you probably, and there are other things more than what I've just explained. But you stop me when you have, okay, when you it's done, because I don't know. Okay, so okay. But as I told you, in linear optics, we have many things that comes out when the field is weak. And so we can use perturbation theory from the theoretical point of view. But we have also the problem that we can kick really very long period, and perturbation theory can't work anymore. And so we have to go beyond perturbation theory, and this is the field strong field. In this case, you start from the time-dependent Schrödinger equation. You have to find a way to solve the time-dependent Schrödinger equation without using of the perturbation theory. So, and I was thinking this. So you mainly solids, maybe not just solids. I will also slightly talk about molecules. But I think it was interesting because in solids there is this strong field that is taking a particular importance in the recent year. To recast a bit non-linear optics. And so just to remember that laser was discovered in 1960. This was the year of the starting year of what was possible in optics. The first observation of second order generation, so all the things I just said before, so started in the 1960s. So you see, this was a schema of what was going on, and then you have these omega and 2 omega, actually lambda, that were measured, which is really a signal of the second order generation. And here I want to come here because in strong field, so I'm really talking about strong field, so really strong laser intensity. In solids, there has been, it is quite recent, in the 1997, the first observation of my, sorry, in one moment. This is too early. this is still, I was too excited to talk about solids, so this is still atoms. We have to wait more time. In the 1997, there was the first observation of HAG. And the HAG is a process, it's a strong, it's a process in the domain of strong field, but the first observation was on atoms. So my project was on atoms. And this is argon. And this is a very strong a process that can happen just in strong field. You can have this spectrum, which you can see one harmonic, two harmonic, three harmonic, and so on. And this is an example of argon HAG spectrum. And then just because it will be explaining this, it will be also more clear to understand what's going on in solids. That will be in a couple of slides. In the 1993, there was this three-step model that was introduced to explain what is beyond ion observation. And basically, you have to think it's a super easy model. You take, and this has been used now, and this model is used now also for solids. So it started from atoms, it is being used for molecules, and nowadays it is used for solid. And what they do, you think that all the physics, this is what they say, that all the physics lies here. So you have your system that is in ground state, no field, just in the ground. Then you apply an electric field. The Coulomb potential change, so you can have a tunnel ionization, so your electron can go in the continuum. It is accelerated in the continuum, like here, but the field, these are oscillating fields, so they change sign. So once it is accelerated, the electric field changes the sign, so it takes the electron back. And once it goes back, here, but once it goes back, it can feel that there was a hole, that there was a parent ion beyond, and then it can be combined and emit this photon that is ion concentration that then is measured. It's a very simple picture, but it was quite well. And in the 2001, there was the first measure. Because of this high spectroscopy of up to second pulses, I set it two articles because one they found this train of up to second pulses. I mean just this train of up to second pulses, and in the other one they have been able to really extract just one pulse of the up to second resolution, and this gave rise to the up to second itself. Here is an example. Because before to arrive to solid, there was all this. I think it's important also to see where the components were. There were a lot of studies on molecules, for example. So the first thing was atoms, then we started to see molecules. Here it is an example of application. They have applied this spectroscopy to tomography. So if you look up, if you take this molecule, this is CO2, and the left, the right one is a code, a program code, normal code, computational code, and the other one is the experimental. That was really that has been measured by experimentalists, and thanks to this resolution of the optosecond that is capable of really they call it light molecular activity because you can see electron in real time because it's in the same range, the same resolution of the electron movement in your system. So this is the strong things. And finally, this is for the solid in the 2011. That was the first observation of HAG in solid. This is the reference article show you. It was done on zinc oxide, and so there was this measurement of HAG, so the strong process. And you can see how you have these peak that are all these harmonic. And there is another thing that is recurrent in this kind of spectrum, is the cutoff. What is called the cutoff? It is the position after which no more harmonic are measured. And it's something that depends on the intensity of the laser that kick your system. And so you see is the green and the blue are just laser with different power, different energy. And starting from here, I think I finish. Starting from here, what is the challenge, in particular from the theoretical point of view, is to try to really understand what's going on. Because in solids, you have this bench structure, things are more complicated than I think in the molecule. Okay, you have this, I propose you some of the theoretical work that have been done for the interpretation of what is going on in solids. You have this excitation, so you have a balance production, and then you can have intra-bench emission. So really some harmonic emission that comes because you create a cavity. Okay? Then you can have, of course, regulation, you can have intra-band emission, and quantum interference. So there are in Italy you can find a very nice article that study this mechanism and try to understand what is going forward. To finish, just an overview of course, Yango, because we are in a school in Yango, so there are many things that I forgot. Mirta will talk just after me, so I think she will give much more detail. I actually she will explain really what Yango will do and stuff. There are other codes that exist, and each of these codes, I will give the presentation so you can get more or less. For example, some are solids, some can be solid molecules, some just molecules. Perturbation theory, non-perturbation theory, from field, real time. So there are many things that you can do, and not all the codes are the same. So just be aware that, yeah, there are many things here you can go off and on. And really, the last two phrases, I think there is a quite, not for solids, but if you define system, I think there is a huge work that has been done in a long time ago. And there are very nice code. I just cited Dalton, but there are many others that are quantum chemistry that really developed very nice theory and also computational code to describe optic effects in a finite system. And if I had some time, I had something else, but I stop. And I would like to thank you and thank the organizer again.
Thank you very much for the introduction, and now the session is open for questions. So maybe I can start with one. So you discussed the case of the antiferromagnetic side. You said that the crystal has a certain symmetry, but then the magnetic point. But I guess you need to include the spin orbit interaction to transfer the.
Yes. We have to, okay. It's not me that I just propose this thing because I think it is a nice example. But I have never worked on chromium precise, so I know that there was Valerie Vignano that we know that, but I have never worked on. And what she did with the PhD students of her, they really included in the chi the spin. So they really do spin-dependent chi, exactly, and the A from the things. Yes. This is what they did.
That's why it's, you won't expect you just down the cell and put this.
For what she did, I think she did like this. Yes, as I said, I didn't. I didn't.
Yeah.
But I think I think it's important. For me, the method was if we take some materials for the students, we take some material, we want to compare with something. We just need to be aware what the kind contains. So we cannot take an experiment to say, okay, there can be electronic contribution, there can be spin contribution, there can be also quantum contribution. So when we do the comparison, I think we just need to be aware of what to do. So this was the message that I took what you just.
So there is a question.
Thank you for the nice talk. You talk about, in thesis, about the layer dependence
Yes.
of the SCAs. What about the stack independent? Any different depending on how you stack the material?
Okay, it's again a very general answer. I guess so. So again, I'm not an expert on stacking or even on strain. What I know is that again, if you do this kind of calculation, again, if you want to compare, I guess so, because as soon as you change your material, something in your material that can change the symmetries of the material, the second harmonic response, in particular second generation, as it is so sensitive to the symmetry of the material, can change. So I would say that if I have to do a calculation on this kind of material, I will definitely pay attention to how the material changed because of the stacking. This is very so I guess.
Yes.
You talked about the electron periodic contribution.
Yeah.
Of the harmonic generation.
Yeah.
I talked about more ionic contribution.
And what about
Ionic contribution.
ionic contribution? Okay, ionic contribution, to my knowledge, then of course there are other people that use maybe they can add. My audience, they really concerning ionic contribution, most of the things done on second generation include electronic contribution. There are few work on electronic contribution, then basically you take there are, I can show you more detail the evaluation, but there are a few work, and I think Yamuda, yes, I remember. Basically, the sum, it is in the article, some, what is the last article? Exactly, Simone Grillo, yeah. So maybe the best person to ask is Maurizia. So there was this work, but otherwise there are no real things that have been done. So
Again, to complete the ionic contribution, you need to displace the other.
yeah, you need for what Lisa did. I think she wrote a Kai2, where she really kind of tailor expansion. She takes into account the change of the displacement of the atom, the coordinate of the atom. So these enter in the susceptibility, which you consider the ionic susceptibility plus the electronic susceptibility.
Maybe there could be a formulation in terms of electron follow count. So
Maybe there can be. I think there can be. I'm not aware that someone did. And I also think that beside that, there can be also some really forms. So there is this displacement, and there are. There are also some phonon breaking that can change your because again, chromium oxide, you can have magnetization, but you can have this phonon fluctuations.
question from the
What about the game? How is that described in terms of this manifest?
Okay, it's a nice question. Okay, when I think of the gauge, I think the strong field. So you tell me, okay, okay. In the strong field, for what concerns solids, but it's probably the things that are less from because I really want more molecules of solid. I think they use mainly the EPC, but I have not seen, maybe it's my quota, so much study about these. In my opinion, concerning solids, there is a huge need of theory development to really understand the mechanism. And so the gauge is between Molecules, it has been studied, and basically what you have seen that if on the paper the two gauges is the same, you notice they are not. And for example, give you some quite good example. In the grid, the people that are great are actually they can converge faster, and they can have a good result in the velocity gauge. Me that I use induction, for us it's impossible to use velocity gauge. We can just use the length gauge. There are some very limitations, but they are definitely not equivalent in practice. One of them, I think none of the two is wrong. I think it's at least for what I've seen in induction. I think it's more the basis, not the gauge. If I was able to compare exactly the same in number of basic functions, so if I was able to do two, I think I can manage. But for some numerical reason I cannot, and one was better than